Okay, so we'll be talking about a protocol. I don't know. Maybe we can see what I wrote. Sha. Forget the forget the handwriting. So we've been able to see how to implement a polynomial, right? And I'm sure like almost all of us have finished implementing like at least polynomial interpolation, polynomial evaluation, right? So there are different uses of, like, you can use a polynomial for different things. You can use it to represent data, right? You can use it to encode data. Like I said in the previous class we had, say you have a long message and you are looking for a shorter way to represent it. You can encode that message as a polynomial and then say share the polynomial to anybody you want to read the message. And if the person wants to now regenerate that message, the person evaluates that polynomial at a certain number of points. I don't know if what I said makes sense. Okay, so let's say I have a message. Hello world. Right? And I want to send this message to somebody in the US. And one thing is that if I send this message over a network, probably, let's say if I send the message over a network, before it gets to the person, the message may become like Jello world or something like that, because probably while the message was in transit, it was corrupted. All right. Okay, forget. So we're looking for a way to be able to send this message to another person, right? Even over a noisy channel. But then when the person receives, or whatsoever thing the person receives, the person is still able to reconstruct back our original message. Hello world. Does the problem make sense? We have a message, hello world. We want to send this message to somebody in the US. And let's say the way we want to send it is by word of mouth. So I'll stand here and I'll shout, hello world. No. Well, it's going to be like a chain. It's going to be a chain of people, right? So I'll stand here and I'll shout, hello world. And maybe somebody at Ibobo will hear me. And the person will repeat, right? Hello world. And it keeps propagating. Yeah. Yeah, so like in the course of transmission of that message, somebody might hear yellow word or jello word or something weird, right? But the idea is that when the message gets to the person in the US, whatsoever thing the person hears, let's say if the person hears yellow word, the person will be able to go back, like the person heard yellow word, but then the person is able to reconstruct our original message, which is hello world. So that's the idea. Here, in this case, I'm the sender of the message, right? We are using a channel. The channel is those people that are repeating the message. And then the receiver is the person in the US. Right. So in that case, like we can think of this problem now in another setting. Like how can we use a polynomial to solve this problem of sending a message to one party, and say if the person gets something different, the person is now able to reconstruct the message. Does it make sense? Makes sense up to this point. Yeah. So one thing we could do, like right now, I've not yet started talking about like Shamir secret sharing. I'm just talking about like using polynomial to encode information. Right. One thing we could do is we could give each of these letters a number, right? Give each of them like an ID, like we did in the distinct case. So one easy way to do it is like, since it's alphabet, we can just do A, we'll give A an ID of 1, B an ID of 2, C an ID of 3. That way, right? I don't want to do the whole encoding, but let's just say everything came out like 13, 5, let's say 12, 12. So 13 is H, 5, 12, 12, let's say 20, let's say 24. They're just random. And so on and so forth, right? So we have this array. We're also going to give the space a number too. We're going to give space an ID. Right. Okay, 0, right? Let's give it an ID of 0. So we now have this long number, right? So one thing we can do is now to get a polynomial that passes through all these points. I don't know if it makes sense. And to do that, we need values of, we take this as values of y, right? Then we need to look for values of x, such that if we pass x into that polynomial, we get y, right? So in that case, if we decide to go with like the normal sequencing of numbers, we can start with like 1, right? 2, 3, 4, 5 to the end, right? So we look for a polynomial such that if we pass in f of 1, we are going to get 13, right? If we pass in 2 to f, we are going to get 5, right? If we pass in 3 to f, we are going to get 12, right? And so on until we get to D, which is world. After we get that polynomial, we can send, okay, after we get that polynomial, we can now evaluate that polynomial at more points. Does this remind us of anything? Error amplification, right? Good. We now evaluate that polynomial at more points. Let's say hello world is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 characters, right? Then say we use a blow-up factor of what should we use as a blow-up factor? 1000. Good. So we use a blow-up factor of 1000. That means after amplifying the error, we are going to have a new array of numbers that is 10,000.
Sorry, what about the space? Are you going to count?
Sorry, the space. We are going to count it. So 11. So that means we are going to get a new array of numbers, 11,000 numbers, right? So let's say it's now this 11,000 numbers that we now transmit. This 11,000 numbers, I want to still send it to the person in the US. We are still using the same method, right? So I mention all the 11,000 numbers, like I shout them out loud. The person at Ibobo hears them, writes them down, and repeats, right? Then we just continue like that until the person in the US gets the message. When the person in the US gets the message, good and fine, our channel was not reliable because someone might have heard something different, right? But because of the fact that we amplified the error, like we did that error amplification, we made room for redundancy, in a sense that we made it possible that even if, say, like each of these processes, they have like their different error correction parameter, right? So let's say, based on this our protocol that we're talking about now, we made it possible that even if 50 of those numbers were wrong, right? Even if 50 of those 11,000 numbers were wrong, the person in the US will still be able to reconstruct hello world. I don't know if it makes sense. Okay, so so let's now like talk a little bit about polynomials and why that is even possible, right? So there are the properties of let's say encoding theory. It's like I'm taking this thing too far now.
From something that's already in existence already, or we're talking about like maybe reversing engineering is trying to like maybe replicate or get back that stuff.
We have a message. We encoded the message, right? And we sent, say, a code word. So the person that receives the code word should be able to reconstruct the message. Does it make sense?
Maybe the message goes from the broken parts of the messages, bring it back together, or they are reforming the message again.
While reforming the message from the code word. Yes. Does it make sense?
So if it's possible for them to code, get the message back, right? What's now the point of sending it? If there's a code word, they could use to actually get the whole messages one by one. Like if I could, there was a way for me to actually fact check everything. Okay, what if in transmission all the words are lost, like everything comes wrong? So I have to check for literally everything. So what was now the point of me transmitting the truth?
No, you don't need to check for everything. Yet. Like there'll be a way for you to know that okay, this code word I've gotten has been corrupted beyond a way I can repair. Right. Like there's usually a bound. Yeah. So if the error is more than you can correct, there is error detection and there's error correction. Right. So if the error is like maybe you detected an error, but then to now correct that error to get the original message back, if it's not like within the bound of that protocol, it will not be possible. They'll need to scrap the whole thing. I don't know if it makes sense. So okay, let me just like go straight like into Shama secret sharing. The whole essence of Shama secret sharing is that we have a secret and we want to share that secret between people, but in a way that only a certain threshold of people can reconstruct the secret. We have a secret, we break it down into different components, right? And we share those components between different people. So we want a situation where that, let's say if we place a threshold of like 3, maybe we have 10 people, we share that secret between the 10 of them. We give them just a part of the secret, not the whole secret. And we want a situation where if the threshold is 3, if 3 people come together, they can reconstruct the original secret. Right? If 3 people come together, they can reconstruct the original secret. So,
And it can be
Any random view.
yeah, any random 3.
Is it like networking? That's error detection problems that you're seeing. Like the way it has CRC, when they send the packet from one client to another, then it's able to only maybe can be reconstructed or not. And you are saying something about breaking it into pieces. So just like he said that anybody can reconstruct it. That's
No, I said any random 3 people can reconstruct it. Since we put a threshold that at least 3 people should be able to reconstruct the original secret.
so it's only broken into pieces.
How do I?
Sorry, you said so we share the secret, split it among 10 people,
Yeah.
such that if 3 of those 10 come together, they can reconstruct the original.
The original. Yes.
Is this similar to how Guardian works on Stacknet, where you can, if you generate a wallet, you can choose to like back it up using Guardian. So what Guardian does is they hash the private key or your mnemonic phrase and split it to different Guardians. So anytime you want to get your private key back, you have to like get those splitted hashes from the Guardians to reconstruct your private key back.
Yeah, I think it can. That works. Yeah.
Sorry.
again.
Let me give an application. Just one application. So imagine if you are 10 in the house, right? 10 roommates, okay? And you guys have this safe. And you guys are always putting money inside, right? Everybody's putting money inside. And this safe has a code
So you want to spend from the safe, you put in the code, and you open the safe, and then you take the money. It's too dangerous for one person to have, for everybody to know the code, right? So tomorrow I might have said that I want to spend all the money there to go and buy pizza or something, right? So I'll just go there, I'll put the code and take the money that everybody has put their hard-earned sweat into. So rather than telling everybody the code, I need to figure out a way to, and we don't know, that's the point of this. Like, how do you solve that? How can you distribute things to people such that if a majority comes together, not necessarily a majority, you guys will decide. So you can say that, oh, if 6 people come together, they should be able to open that safe. Any 6. If you can also say if 3 people come together, they should be able to open that safe. So you choose your threshold, and then once that number of roommates come together, you can figure out the code to unlock the safe. So the question now is like, what do you give each person that will allow them to do that? Or let's say nuclear codes. You want to throw nukes. You don't want one person to know the code to the nuke. So maybe you want like 3 officials to be there before you can get the code. But then you have like 50 officials. So you give 50 officials something. And then once any 3 comes together, they can use that something to get back the code. But if only 2 come with their something, they should not be able to get that code. If 3 or more come together, they should be able to get the code. That's it. Those are like some practical applications of what you shall not secret share. So you can use it to hide any secret behind multiple things.
Okay.
Yeah.
So does
Yeah.
yeah. So does it make sense? Another way to think about it is like most of us here are like smart contract devs, right? Like a multi-sig wallet, right? Where like there's a threshold of people that can sign in order to release money from the wallet. So if we don't have people up to that threshold that agree, we won't be able to send money, right? I think the multi-sig is makes more sense, right? Okay. So there's one way that we can go about this, right? Using polynomials. And for that, we can decide to, okay, let's say an example, right? We have 10 people. We have 10 people that came together to contribute. And whenever we want to disburse money from that, maybe Ajo, Abi, that's what they call it. So whenever we want to disburse money from there, we need at least 4 people to agree. Like 4 people out of those 10, we need at least 4 of them to agree. We need at least 4 people to agree. So, and those 4 people can be like any random combination of the original 10 people. One way we can go about this is to define, let's say, a set of points on a curve, right? Let's say 3. We define a set of points on a curve. And then we use this set of points to construct a polynomial. let's say this is what the polynomial looks like. We can remember that, let's say a polynomial of degree 5, how many points can we use to represent it? 6 points, right? So if we have 6 points, we'll be able to, like 6 points is a minimum number of points we are required to have to be able to generate the polynomial, right? How about a polynomial of degree 10? We need 11 points to be able to reconstruct the polynomial. So if, let's say we have a polynomial of degree 10, but we have the evaluations of that polynomial over 20 points, will we still be able to reconstruct the polynomial of degree 10?
Yes.
We will, right? Okay. How about if we have just 9 points? Will we still be able to construct a polynomial of degree 10? No, right? Okay. So let's say we want our secret to be the evaluation of one random polynomial at f equal to 0. So let's say at f equal to 0, we want our secret to be maybe, let's say, can anybody give me any random number? Huh? Okay, no, a random number. Okay. So, like 17 in this case is our secret. Okay. No, like 17 is the secret, that is the password that we can use to withdraw money. Right. You know,
One of the passwords or just the password?
no, just the password. 17 is just the password we can use to withdraw the money. Right. But we want a situation whereby if 3 or if 4 people come together, they will be able to get back this 17. Okay. So, can anybody think of like how we can go about like defining a polynomial and using this to come up with like a situation where if 4 people come together, they will be able to get, like, let's say everybody knows that the secret is the evaluation of one certain polynomial at point 0. Right? The idea is now like, how can we get that polynomial? Can anybody try?
We don't know the polynomial, right?
Yeah, we don't know the polynomial.
But we know the
Do we
point.
know the degree?
Do we know the point?
The points.
The degree is given already. 3.
Yeah.
How many of the points do we know?
We want 4 people to be able to come together to get back a polynomial that if we evaluate it at 0, we are going to get 17.
People as in points, right?
Yeah, we can think of, because we are giving a point to
So we're looking at
everybody.
people as points. Is that what you're saying? So we're supposed to like have 11 points. Now you're saying instead of 11 points, we're using 4 points. Is that what you're saying?
No.
I feel we can give each and every person one point. So if 4 of them can come together, they can just easily get the number.
If you give 4 people 1 point and they come together, it's still 4 points.
No, everybody is 10 people, right? So give each and everybody one point. When 4 people come, they can easily
At
get
least.
Yeah.
At least.
The idea is that 4 people come together and then they sum it together, they'll get 76.
That's a 3-degree polynomial.
Yeah.
So the point is that we don't have to know how many people. Like, if it's possible, if we know, fine. But if we don't know, we don't have to worry about it. How many people we just need a subset, which is 4 people given to us that must come together. So already that suggests to us that no matter the degree of the polynomial, whatever, if you are using interpolate, you collapse it to 3 to get the point. So what we should worry about is the points given to get the polynomial. So the question Jude asks is very valid. Are we giving the points?
You can generate random points. Like you can generate random points on your own. I don't know if it answers your question.
Do we know the
How do
degree
we
of
go
the
about it?
polynomial?
Okay, wait.
So, like, now.
Sorry, the degree of the
Yes,
polynomial.
do we know the degree?
No, we don't know the degree.
So, what I think I was going for
No, we've said we want 4 people, right, to be able to generate it. So should I still tell you the degree again?
So like now, the thing is that you have like a maximum of 11 people that you want to share a key with, like share keys with, right?
Yes.
You want minimum of 4 people to be able to come together to open, like to be able to like get the secrets.
Yeah.
So what we're looking for now, we have like, okay, let's say we have a polynomial already that forms this 11 points.
Okay.
Right?
Okay.
Do we have that already?
Just continue.
Okay, so if we have so if we have that, let's say, so now we want to generate a polynomial, like a secret. Like, okay, let's say the secret is going to be 17. So we want to generate a polynomial that any 4 points picked from those 11 points can give us this 17.
Okay.
How do we go about creating a polynomial?
How are we going to create a polynomial?
I'm thinking that
Is
if
it?
you're pegging,
Yeah.
Since
Sorry.
we need 4 people to be able to unlock it. We can generate the points from whatever secrets you have there. We create a polynomial from those points through interpolation. So once those 4 people bring that point, if any 4 people from any random function bring that points together, they can create the polynomial back and then evaluate it at point 0 to get 17.
Yeah.
If you try
I
to
don't
do
get
that,
what
right?
you said.
Yes.
Yeah, that's actually.
Please, can you
Can you repeat it?
Okay, so you need at least 4 people to unlock the stuff. So just create the degree polynomial from a set of points from the secrets. Like after we divide it. So create a polynomial of degree 3 since we need at least 4 points. So once any 4 people with valid points on that particular polynomial come together, they're able to create the polynomial and then evaluate it at point 0. So through interpolation they create the polynomial. Evaluate it down. That's all.
So 4 people will evaluate at 0.
No, nobody. Those 4 people will construct the polynomial.
Are you seeing everything?
Interpolation methods, yeah, but you control the polynomial from 4 points.
So that means
Okay.
the value not always be like
So is it that one you're not evaluating?
The value.
yeah.
Of.
Like when the polynomial is evaluated, the value will not always be the same thing. But the value you're going to get will always be on that curve.
I didn't get
Like,
to.
if you have 4 different points now, if you evaluate, if you get the polynomial, right? If you evaluate like if you have 4 different points, we have 4.4, like 4 different people, A, B, C, D, and you have another one like 4 different people, let's say B, C, D, B, C, E, B, C, D, right? So if you are like evaluating the polynomial, right, you're not going to get the same values. Are you going to get the same value?
If it's the same polynomial, then you'll get the same values.
But yeah, from those 4 different points, you're not going to get the same
Four
value.
different
points
points.
Yes, if you have points A, B, C, D, 1, 2, 3, 4, 5, 6, 7, 8, and you have points B, C, D, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Those 4 different points will not generate the same polynomial.
If
they are
Yeah.
voting from that polynomial, remember that we said that no matter the point given to you, it will always give a unique polynomial. That is
Of
the
that
uniqueness
particular
of
degree.
polynomial.
Exactly. A unique polynomial. You know we have now we're getting like a curve. A curve has a
Okay, let's assume we have a polynomial. Let's say s squared plus 2x plus 3. S squared plus 2x plus 3. Do you know that already we know that at point we can if we get like 5 points from that distance, if we can draw it, I will show you 5 points from it. So from that 5 points, you know already I just need 3 to get the polynomial. I need 3 points to get the s squared plus 2s plus 3. And I have 5 points already in the graph. I can pick any of the 3 randomly from that 5 points and it will still give me this thing.
Exactly my point, right?
Yeah. But yesterday we established that you can have as many points, but we only have one particular polynomial and one particular degree passing through the same points of the same degree.
Exactly.
So it is always, as long as let's say you count like 10 points, but you only have one particular polynomial, one degree passing through the same points.
That's my point, right? You know that now we are saying that we have like 11 random points we are picking, right? Because we have 11 people that want to share secrets to, 11 people want to share secrets to. And then from those 11, okay, we have 10 people want to share secrets to. Yeah, 10 people, right, want to share secrets to. And then we're generating 11 random points, right? So for that 11 random points, you're going to get a unique polynomial. Now, any 4 people, right, from those points, 4 out of those guys will not give you the same polynomial.
Exactly.
Sorry.
Yes, you're right.
No, like I think if you look at it from a linear.
Sorry, wait. Let him finish his question.
So my question is now if these four different guys get a polynomial and then another 4 different guys get a polynomial, right? So whatever the value that they get, right, if it's evaluated at 0, whatever value you're getting is always going to be on this, like it's always going to like land on this curve for the 11 points. Is it going to be that way?
That is only possible if you don't know the degree of the polynomial.
Okay,
We have already been
everybody.
given the degree of the polynomial. We're
That is
told
what
that
is
Let's
possible if the degree of the polynomial is not.
let's calm down. Let's calm down. Your question is that we are picking 11 random points initially, right? We pick, let's say, but just 11 random points, and we give these points to 11 different people or 10, and let's say this is the curve that forms those 11 points. There are 4 people with points on this curve cannot regenerate this polynomial. That's what you're going at, right? And do all of us agree with him? Yes, that's 100% true, right? But in a situation, we put a threshold, right? That threshold was there for a reason, and that threshold is we want only people up to the threshold to be able to generate the polynomial that stores the password, right? So in that situation, is the polynomial we are meant to form supposed to have a degree? This now a general question. Is the polynomial that we are supposed to form supposed to have a degree of the total number of people minus 1, or the polynomial that we are supposed to form, is it meant to have a degree of the threshold minus 1?
threshold minus 1.
Why?
Because at the end of the day, if we have a polynomial of total number of people minus 1, there is no way you can get a reduced amount of number to give that exact polynomial. So, but if you have a polynomial of threshold minus 1, then any
Extra points from
extra
that polynomial.
arrangement of like for example 3, any 4 we generate that, we come down to that particular polynomial.
So is it such that what we are looking to find now is a polynomial that any random 4 points, any 4 points you pick, that polynomial, when you evaluate any 4 points you pick at 0, they will give you that secret number. So we want to find that such polynomial, such that any 4 points you pick.
Is it 4 points or at least 4? I think there's a difference.
Is it
At least.
That would be much more, but probably that, okay, at least 4 points, you give 0. So I don't know how I'm going to develop that, but that's what we want to get right. Like, okay.
Well, you're saying you don't know how, but I thought
So
it's
there's,
credit
I
time.
think there's an assertion that was made earlier that if you have a degree of polynomial, you need at least the degree plus 1 of points before you can generate that polynomial. So given that assertion, if they say we need at least 4 persons to come together before they can open the log, that means the criteria for generating that polynomial is 4 persons, which means automatically if we want to get back the degree of that polynomial, is to deduct 1 from that criteria, so we get the degree. Now, and we know once we get the degree, we can come up with a polynomial which we can, let's say, interpolate and do the rest of.
But now this is the thing. If we have like 6 people, for example, you say more than 4, right? Even if we have 6, it's still 4 that will be used eventually. The rest to be discarded.
That is the error amplification. Because once you have the polynomial, you can just add any point and
so
you get other
it's
numbers.
still 4 that will be used eventually.
Yes.
Is that?
Okay.
That is why at
As
least
long as they degree.
I thought if you use 6, Lagrange you have 6 back.
Okay.
So you definitely have points evaluation of the polynomial now, not
Okay, so let's say something like, what is the degree of this line? Huh?
Yeah, just 2.
one.
1, right? This is a straight line, right? And the equation of a straight line is mx plus c, right? So a straight line is basically a polynomial of degree 1, right? And this polynomial of degree 1 is made up of how many points? 2 points. How many points are on this line? Infinite number of points, right? But in order to reconstruct this line, how many of those infinite number of points do I need? Just 2, right? Okay. Let's move over to s squared plus 2x plus c. Sorry, ax squared plus bx plus c. This is a polynomial of degree 2, right? How many points do I need to represent this polynomial? 3. There can be any 3 random points, right? Why?
Sorry, I have a question. Just based on this now.
Yeah.
3 random points, but this one you chose now, would it be sufficient if you're trying to rule it yourself? You won't be able to get that curve. So shouldn't it pass at least that middle? Abi?
It doesn't necessarily.
If you're trying to play the graph.
You know, it's a quadratic, right? And what's the rule of a quadratic? It mirrors on the y-axis, right? So if we know this point, that means we know this point, right? If we know this point, that means we know this point, right? Which is just the negation. If we know this point, then we know this point. So automatically, with these 3 points we have, we can get it. Does it make sense? So there are still infinite number of points on this curve, right? But to reconstruct this curve, How many points do we need?
3.
3. Right. Okay. So now let's take this idea back to our question. We want to share, let's say, passcode between 10 people, right? But then we want a threshold of 4 people to be able to regenerate, say, the polynomial that when we now evaluate at 0, we'll get the secret. So let's say we come up with, so basically the idea is to come up with a polynomial with how many of degree what?
3.
That is, how many points are we going to now use to represent that polynomial? 4 points, right? I don't know if this is what the polynomial is going to look like, but people should bear with me. So after getting this polynomial, there are infinite number of points on this polynomial, right? And we can still sample more points from this curve. True or false?
True.
We can still sample any random number of points from this curve, right? And out of those points, how many of those points do we still need to reconstruct this polynomial?
4.
4, right? And we want a situation where if we evaluate this polynomial at, say, 0, let's say here is 0, right? It should give us 17. Does it make sense? So after this point has been distributed between everybody, we need only 4, at least 4 people to be able to come together to reconstruct the polynomial. If 3 people come together, would they be able to reconstruct this polynomial?
No.
But would they be able to reconstruct a polynomial?
Yes.
They will be able to reconstruct a polynomial, right? But it's going to be a different polynomial. And if we evaluate that polynomial at 0, we are going to get something different, right? How about if 9 people come together, like not necessarily the people that we gave the secrets, maybe 4 or let's say 3 people from the people we gave the secrets come, and then somebody just came with a random point. Would they still be able to generate this polynomial? No, they won't, right? Why? Because of that one random point. That one random point is not on this polynomial. So we won't be able to reconstruct this polynomial from that set of people. Does it make sense?
Yes.
So the whole essence of Shamir's secret sharing is to enable people to share a secret. Let's say you can take your secret and you can share it between different people. I know I'm saying it this way. Like you can take your secret and share it between different people, but then you can have a threshold of people that come together, and when they come together, they should be able to reconstruct the secret. With everything I've said and what I just said now, does what I said make sense? It makes sense, right? And what protocols would you need to, I won't call you what protocols, like we already have like our polynomial implementation, right? So with our current polynomial implementation, do we think this is something we can we can build. What and what do we need to come up with this? We need interpolation, right? Why do we need interpolation? To be able to construct the polynomial, right? And what else do we need? We need evaluation, right? Why?
We need to evaluate the points.
To get the secret, right?
And the shares too, right?
Yeah, and the shares also, because we need 4 people. We will need 4 initial points to generate that polynomial. But then to get the other points for the 10 remaining people, it has to be on that code.
Yeah.
So the way we can get it is to evaluate that polynomial we got at different other random points, right? So evaluating that polynomial at other random points will still give us points, like random points, but random points on that core. So that if any of those people, like up to the threshold, come together, they will still be able to like regenerate the original polynomial.
Those numbers, like the 11 at first, are they truly random? Or those are just like
Where it can't be.
Which the first 11?
Yeah, that you're actually picking. I feel like
There's
have thoughtfully picked those numbers such that any 3. Because I just saw something now. You said we needed 4 bar to get that f of 0 to be 17. What's the place of coincidence where I can use even 3 numbers and I still get f of 0 at 17? Could that happen? That even when we have 2 numbers or 3 numbers that are even less than the threshold, when I evaluate it at 0, I still get 17. Is that not possible?
That's possible. That's like, let's say there is a degree 3 polynomial that if we evaluate at 0, we are going to get 17.
You just don't, it could be random and it could mistakenly.
But it's same thing as guessing.
Yeah.
What's the probability?
Yeah, that's
Yeah.
that is same thing as guessing. So you shouldn't be worried about that.
But if we are sharing the secret, we should worry about
No, how would they?
because let's say if we have everything set, like we have everything set to get the secret, we can just set it up and run everything. For every result we try it on the key. For every result we try it. So we just use a very powerful computation and just pass as it's running through the process, it's trying it on. So once it gets it, it's going to open it.
Then you don't even need all this. Why not just run all, like, why would you even bother yourself with calculating again?
But I think if it's a large
For every number less than
Like closer.
No. The threshold is not what matters. Okay? The secret can be anything, right?
Yeah.
Like I said, the secret is 1, 2, 3, 4, 5, which is a 5-digit number, right? That could be my secret. The threshold is not related to that, right? So that's the pin for my safe. So now we're saying that there's an easy way to get the pin if you do things correctly. Right? Like you bring the correct shares and everything. But then there's also a brute force way. Like if you just see a safe in front of you, you could literally just try all possible things. So now you need to look at the security. So like 5 numbers, if they're all digits, then you have 10 options for each digit, right? So that'll be 10 raised to the power of 5. That's 1 with 5 zeros behind. That's how many combinations you need to try. For a computer, that's easy, right? So that's not secure. Whether Shamir or not Shamir. You are just using an in. That's like, it's just not a secure safe, right? But then you choose the security to be large. So let's say a safe with 100 digits, or a safe that you cannot apply a computer to. Right now, safes are not secure because they are small. But they know that you cannot just use a computer on it. You have to be a human and you have to press it, and that will take long. So you need something that has high security. And once you have something that has high security, you now choose your pin. Once you choose your pin, you set it to f of 0. then you randomly find a polynomial that fits your threshold. So if your threshold is 4, you're finding a degree 3 polynomial. Once you have found a degree 3 polynomial, you now sample multiple points from that based on the amount of shares you want to distribute, right? So you want to give to 20 people, you pick 20 points, but don't pick f of 0. Like imagine giving someone imagine giving someone 0, your pin. Like just make sure that you don't give anybody the 0. So you give them anything other than 0. Then once any 4 come together, since all 4 points exist on this, you'll be able to reconstruct this. And regardless of the 4 points, it's always this. So the 0 will always be the pin. Then you just evaluate at 0 and get your. So the security, what you're saying is not different from those first.
Yeah, so from what you said, I was just smiling because when you say that the seeds they are not secure because you need to be a human. So I was just thinking about if someone was like going into like what's it called? Where you program hardware, you can just program the hardware, run your stuff.
You could. Because you'll be limited by the speed of your.
The
hardware.
Yeah.
How fast can it?
Press it?
Yes.
But it's possible. It's really possible. It's not high at all. If you don't want to do unless the safe has security measures in, like you try more than
Can you ask everybody?
Okay, so my question is, outside the 4, for instance, we have the 4 value points. If we introduce 2 extra points that don't fall within that, will you be able to reconstruct the polynomial?
Okay. No, we want it to be a different polynomial. Everybody understands why it will be a different polynomial, right? Okay, so like how many of us have implemented interpolation? Okay. So the next thing to add to our bucket list will be Shamir secret sharing. Well, I meant to implement the Shamir secret sharing, the protocol, right? The design decision is yours, right? Anyhow you want to go about implementing it. But the goal is that you should be able to give at least you should be able to define your protocol where you give a threshold and the number of people you want to generate the random points for, right? And then people up to, or at least up to the threshold, when they come together, they should be able to like regenerate the polynomial and get the secret. I don't know if you.
Are we doing it in Rust?
Yeah, in Rust. Yes.
Just like that.
Just like that. There are different ways to go about the implementation.
Can't you just dwell on this one first?
You have not understand the interpretation properly.
So that
you need to understand the guidelines to do this.
The flow.
No guidelines, no flow.
Okay, let's come up with the flow in class. So it's all explained. Yeah, over the weekend.
So what of people have not implemented?
You have Saturday and Sunday. We did it in how many hours?
no, you did it in
We did it now.
have to understand this.
There's something cool too. There's something. Like you could put a password. You know, this is like a distributed. One application of this is like, let's say you have your private key, right? And you want to hide this in plain sight, right? So what you could do is like put your private key at 0, right? And then you could generate shares, let's say like 5 shares or 6 shares. And your goal is that once you bring 3 of those shares, you can get back your private key. Then you can now take those shares, and there's a way to put things inside images, right? So you could put a share inside an image, 5 images. Then just post it on one on Twitter, one on Facebook.
Real wallet.
Yeah, your real wallet.
Money side.
I'm serious. One on Twitter, one on Facebook. Wait. You now distribute it everywhere, right? So people see it as a regular picture, right? Even people that know what Shamir TV sharing is, they might now, let's say, go to all your social media, right? Find all your pictures. Let's assume that they were able to find the 3 that were needed. So they are able to reconstruct your polynomial. Now, there's something that they know. They know that you put the secret at 0, right? So this is what I'm talking about, a password. You don't need to put it at 0. That's not compulsory. You could put it at any point in the polynomial. You could say f of 1 million, 1.9. So unless they want to now put force,
They won't even know that something.
so that's 2 layers of security. First of all, they don't know that your share is in the picture. Then even if they know, and even if they're able to now find the exact pictures, which is already hacked, they still don't know the exact thing. So different levels of security.
First you hide the existence of the
That's why you have more.
Yeah, let's say you lose more than half of the threshold.
If you lose more than your threshold, you have lost your
fun.
Don't lose more than your threshold. That's why you add redundancy. So if you want just 3, you can create like 15 and just put it. But then you need to be careful.
Please, let me get this. You say if they actually get the amount that is required,
And they get the exact one.
they still can't get it.
They will still be able to. Like if the brute forcing space is really large. So let's say the possible keys are just like 0 to 10. Obviously they'll just try everything and say the one that is correct. But if let's say you're using real numbers, and real numbers are like infinite, you could have picked any one of those numbers. Unless they want to start going from, which will take years, they cannot brute force your secrets. You get one? So it's just like security analysis. How fast are computers now? How many numbers can they crunch per second? You can know how many.
Oh, we have quantum computers.
Even quantum computers, right? At some point, they will still need to verify that the secret is correct, right? Like every time, you can always evaluate at 0 and you get a number. How do you know that that number is the secret? So they need to now also like go and log into the blockchain explorer. So there's still a bottleneck. You need to check it for each. So the quantum computer cannot just see the number and say, oh, this is it. You need to test, and that test is slow. So that nullifies the speed that the quantum computer can bring into the picture. It's only if the quantum computer is looking for a specific thing, and you can see it in something.
It must not be own number.
So you can do it without whole numbers, but I think there's a problem with when you're doing real numbers. Yeah. No, you're supposed to use a finite field to do this. Everything in cryptography is finite field.
So real number is a field.
But it's not finite.
Okay, finite one.
We need to move to
Finite fields
finite
are
fields.
fields,
That will be the next thing.
but there's a limited number of numbers, so it's finite. Just like name
So you can put
finite
passwords.
field. It's a
If you
field, but
doesn't have to be
finite.
So who determines
So therefore, our wallet now, don't pay for it.
Yeah, you can determine. For different, just like working mode, working mode, mode 97. So that mode now is 65. You're working with only numbers from 0 to.
How would they know the images? How would they know?
I won't tell
If
people
you
now.
post any tweets now, we'll be checking.
Okay, so what do we know how to go about this? Serious? Okay, does anybody know how to go about this? So nobody.
Explain on this one so that we can understand. They can use it to implement anything in that church. Next class.
Like design section. Like
You can't get an approval once you tell them.